All right, let's dive in. Today, we're opening up the organic chemistry playbook to talk about two of the most important players out there, aldehydes and ketones. We're going to look at exactly how chemists actually build these molecules, step by step. You know, it's a huge question, right? But the answer, a lot of the time, starts with simple, reliable reactions. Aldehydes and ketones are these incredible building blocks for just about everything, from the fragrances you smell to the medicines you take. Knowing how to make them is an absolutely foundational skill. So here's our game plan for today. We'll start with a quick refresher on why these molecules are so important. Then we'll jump right into the synthesis playbook. 4 methods for aldehydes, 3 for ketones. We'll take a quick peek at their physical properties, and then we'll wrap it all up with the big picture. Sound good? Let's go. Okay, section 1. So before we get into the how, let's just double down on the why. These compounds are right at the heart of countless chemical transformations. That's what makes them such essential players in the whole world of synthesis. And now for the main event, the aldehyde playbook. We're going to break down 4 super reliable methods for making these molecules, and we'll kick things off with a classic named reaction. So our first place starts with a really reactive molecule called an acyl chloride. You can almost think of it as a spring-loaded version of a carboxylic acid, just primed and ready to be transformed. And the special move we're going to use is called the Rosenmund reduction. And here it is in action. See that benzyl chloride on the left? Well, by treating it with hydrogen gas and this special palladium-barium sulfate catalyst, we can selectively swap out that chlorine atom for a hydrogen. And just like that, bam, we get our final product, benzaldehyde. It's a really clean and direct way to get the job done. So the recipe is simple. You start with an acyl chloride, you use the Rosenmund catalyst, and you get an aldehyde. Now, here's the really clever part. That barium sulfate is actually there to poison the catalyst just a little bit, to stop it from going too far and reducing the aldehyde all the way to an alcohol. Pretty smart, huh? Okay, let's move on to our next starting material, nitriles. These compounds, with that funky carbon-nitrogen triple bond, are another fantastic launch pad for making aldehydes. And we've actually got a couple of ways to do it. The first route is called the Stevin reaction. You can think of it as a 2-step dance. First, you reduce the nitrile down to an intermediate called an imine. Then, you just add water to hydrolyze that imine, and it turns right into your aldehyde. You can see both steps of the reaction right here. First, the nitrile, that's the RCN, reacts with tin chloride and HCl. That gets you to the imine intermediate. Then, you add water, which breaks that carbon-nitrogen double bond, giving us our final aldehyde, the RCHO. The Stevin reaction is a great choice, a real classic. But it's not the only game in town when you want to turn a nitrile into an aldehyde. There's a more modern approach that uses a different reducing agent, which gives chemists a bit more flexibility. And that brings us to this other popular reagent, diisobutyl aluminium hydride, or let's be real, we all just call it D-H. It does the exact same transformation. D-H reduces the nitrile to that imine, which then gets hydrolyzed to the aldehyde. It's just another powerful tool for the same job. Okay, let's switch gears. What if you want to make an aldehyde from something really, really simple, like a basic hydrocarbon? Well, we've got 2 great ways to do that, especially if you're trying to make benzaldehyde. So here we're seeing 2 different paths that both start from toluene, which is just a benzene ring with a little methyl group attached. On the left, we're using chromyl chloride, and on the right, chromic oxide. Both are oxidation reactions that carefully turn that methyl group into an aldehyde group. Same starting point, same product, just a slightly different flavor of reagent. And for our 4th and final method for aldehydes, we have the Gattermann-Koch reaction. Now this one is really cool. It takes a plain old benzene ring and, using carbon monoxide and HCl with a catalyst, it slaps an aldehyde group right onto it. This is an awesome way to build complexity from a very simple base. All right, we've covered aldehydes. Let's pivot to their cousins, the ketones. The playbook here is going to look a little familiar, but there are some really crucial differences in the reagents we use. So you might be thinking, hang on a second, didn't we just use acyl chlorides to make aldehydes? And that's a great question. You're absolutely right. Our first starting material for ketones is an acyl chloride. So how do we make sure we get a ketone this time? Well, the secret is all in choosing a very specific kind of reagent. The new player on the field here is dialkyl cadmium. So instead of that palladium catalyst we used for the Rosenmund reduction, we use this organometallic reagent, What it does is deliver an alkyl group to the acyl chloride, kicking out the chlorine and forming our ketone product perfectly. Now, this special reagent isn't something you can just grab off a shelf. You actually have to make it right before you use it. It's a two-step process. First, you take a powerful carbon-based tool called a Grignard reagent and react it with cadmium chloride. That creates the dialkyl cadmium. Then, you take that freshly made reagent and add it to your acyl chloride to synthesize the ketone. And just like we saw with aldehydes, we can also make ketones from nitriles. But again, the reagent choice is what determines the final product. Instead of a reducing agent, this time we use a Grignard reagent. It attacks the nitrile carbon, and after a little water workup, we get a ketone. It's a perfect example of how one starting material can lead to totally different products just by changing what you react it with. For our final method, we're going back to benzene rings, and we're bringing out one of the most famous reactions in all of organic chemistry, Friedel-Crafts acylation. The whole goal here is to stick an acyl group, that's the RC double bond O part, directly onto an aromatic ring. And here it is. Benzene reacts with an acyl chloride, in this case, acetyl chloride, and you need a Lewis acid catalyst, like aluminum chloride, to make it happen. The result is a direct attachment of that acyl group right onto the ring, forming an aromatic ketone like acetophenone. This is an incredibly important method for building complex aromatic molecules. Phew, we've covered a ton of synthesis. So let's take a quick breather and look at the physical nature of these compounds. I mean, what do they actually look and feel like in the lab? This table gives us a great snapshot. The simplest aldehyde, methanol, you probably know it better as formaldehyde, is actually a gas at room temperature. The next one up the chain, ethanol, is a volatile liquid. And as the molecules get bigger and heavier, both aldehydes and ketones are usually found as liquids or even solids. Okay, let's zoom out and pull all of these threads together. What are the key lessons we can take away from our synthesis playbook? When you boil it all down, synthesis is really all about strategy. We've seen that named reactions like Rosenmund and Friedel-Crafts are like trusted recipes in a cookbook. We learned that the choice of reagent is absolutely critical. It's what lets you turn an acyl chloride into either an aldehyde or a ketone. We saw how versatile starting materials like nitriles can be. And finally, we explored some really powerful tools for building directly onto aromatic rings. You see, these reactions aren't just abstract concepts on a page. They're the actual tools that chemists use every single day to build the world around us. So the real question is, with this playbook in your hands, what would you want to create?